Let's do another example, and again we're going to find the reactions and draw the shear and bending moment diagrams. Here's our beam. I've got 3 loads on it. These are the dimensions. And what we're going to do, of course, is we're going to I'm going to let you do the reactions, but I take the sum of the moments about A equals 0. I get By as 17.5 kilonewtons. I take the sum of the moments about B equals 0. I get Ay is equal to 12.5 kilonewtons. And I, just as a check, I look at it, and what do I find? I have the sum of these two, which is 30 kilonewtons going up. I have the sum of these three, which is 30 kilonewtons going down. So I have that up equals down, and that gets me to gives me confidence that I have the right answer. And now I'm going to draw the shear and bending moment diagrams. And if you remember what we're going to do to get the shear diagram, we're going to use the arrows. To get the moment diagram, we're going to use the areas. So let's start with the shear diagram. You can see I have all these arrows here. Okay, so we're going to use those. I start at 0 for the shear diagram, and that arrow says go up 12.5 kilonewtons. Then I go straight across. That arrow says go down 5 kilonewtons. I go straight across. That arrow says go down 10 kilonewtons. I go down 10 kilonewtons and then straight across. That says go down 15 kilonewtons. I go down 15 and then straight across. That says go up 17.5 kilonewtons. I end up back at 0. So just to emphasize it, I'll do it one more time. So I start at 0, I go up 12.5. I go down 5, which takes me to 7.5. I go down 10, which takes me to negative 2.5. I go down 15, which takes me to negative 17.5. And then I go up 17.5, that takes me to 0. So now I'm going to get the areas. So I break this up into rectangles. So for the first rectangle, the area is 12.5 times 3. I use the 3 meters, and I use the 12.5 kips. I haven't shown the units there, but I should show the units. So remember that the units on shear force, or sorry, not kips, kilonewtons. We are in metric here. And then the units for the moment are kilonewton meters. So with those units, to get our areas, I have 3 meters times 12.5 kilonewtons for that one. This one is going to be 3 meters times 7.5 kilonewtons. This one is going to be 3 meters times negative 2.5 kilonewtons. This is going to be 3 meters times negative 17.5 kilonewtons. Those are my areas, area 1, area 2, area 3, and area 4. So I'm going to use these values. Okay. So I start at 0. My A1 is 37.5. I go to 37.5. Then the next area is 22.5. So again, I'm working left to right, so I add that in, another 22.5. That takes me to 60. Then I have negative 7.5. It takes me to 52.5. And then I have negative 52.5, which takes me down to 0. And we know the slopes of these lines because if you remember the slope of the moment diagram, the slope of the moment diagram equals the value of the shear diagram. So the value of the shear diagram in that entire region is 12.5. That means the slope everywhere on the moment diagram in that region is 12.5, which means it's a straight line. So the slope is 12.5, and then similarly the slope here is 7.5. The slope here is negative 2.5, and the slope here is negative 17.5. So I know all the slopes as well. We're going to make use of that as we go along. And so very quickly, notice how quickly we did that. Within a couple minutes, we were able to get the shear and bending moment diagrams. Now, what is the value of this? We've done the shear and bending moment diagrams, but why are they valuable? Well, first of all, is that I can look at let's look at the shear diagram to begin with. And what do I find? By creating the shear diagram, I can see immediately the greatest shear. It pops right out. I look at it and I see, oh, we're looking at the greatest maximum absolute value in this case, and I see the greatest shear is, in this case, negative 17.5 kilonewtons. And I know that it's in this region of the beam, so it's over in here. So if this beam were going to fail in shear, then it's going to occur in this portion of the beam. Why? Because under this loading condition, that region has the greatest shear, assuming the beam is basically homogeneous throughout. I mean, in other words, it's the same beam everywhere. So it takes us only a second to recognize that. Now we look at the moment diagram, and the same thing. I can immediately see the location of the greatest moment. The greatest moment is 60 kilonewton meters right there. So what does that mean? That means that this location in the beam, if our beam were going to fail in moment, it would be at this location right there. Right? In this particular case, it's the center. So one of the beauty of the shear and bending moment diagrams is that it pops right out at you. And when we design our beam, I need to design for that 60. I need to design the beam for this negative 17.5. So it pops right out at us, and we can see the problems that can occur and immediately, and that's the beauty of the shear and bending moment diagrams. Now notice that we can see obviously that the shear force varies across the beam. It's not constant. That shear diagram shows us very clearly that the shear force in the beam is not the same everywhere. And similarly, we find that the moment across the beam is not the same everywhere. There's some places it's worse. Now, if we go back to our trusses, for instance, and our cables, we didn't have to do this for cables. We didn't have to do this for trusses. Why did we not have to do it? Well, let's go back to that when we were talking about we're talking about trusses. We're talking about cables, and if you remember, what did we decide? Well, when we have our cable, the tension in the cable was constant. In other words, the tension here is the same as the tension there, is the same as the tension there, is the same as the tension there. We didn't have to worry about where the cable is going to break because the tension, in theory, is the same everywhere. So we didn't have to draw any sort of diagram to figure out where the greatest tension was. It's the same. Same thing with a truss member. You know, the force in the truss member there is the same as there, is the same as there, same as there. So we didn't have to worry about, in a sense, where the truss member is going to fail because it's the same everywhere. So a beam is different from that, and a beam has a different shear force, a different moment, and that is why we have to draw the shear diagram, why we have to draw the moment diagram, because those forces and moments are not constant throughout. There are places where it's greater than others. All right, so I want you to do this problem, and you should be able to do it very quickly. Draw the shear and bending moment diagrams and label them. And in this case, I have given you the reaction. So pause the video here and do this problem. It should take you just a couple minutes to do it if you're getting good at it. All right, I'm assuming that you've done that, so it's quite straightforward. Again, I follow the arrows to get the shear diagram, so here are my arrows. And I start at 0. That says go up 15, straight across. That says go up 8, straight across. That says go down 52.3. I go down 52.3, and then straight across. That says go up 29.3. It takes me back to 0. So, in terms of the values, what do? I start at 0, I go up 15. Then I go up 8, takes me to 23. Then I go down 52.3, takes me to negative 29.3. Then I go up 29.3, takes me to 0. So I now have area 1, area 2, area 3. And what do I have? That's 6 feet times 15. 90. That's 5 feet times 23. 115. This is 7 feet times negative 29.3. Negative 205. Start at 0. I go up area 1, so I go up 90. I then go up another 115. Takes me to 205. And now I go down 205. So did I do it right? Hopefully I started at 0. I ended at 0. So you have to do that. If you don't end up at 0, you made a mistake. It's going to be like that for every problem. You start at 0, you end at 0. I know the slopes. I know the slope there is 15 because the value of the shear is 15. I know the slope there is 23 because the value of the shear is 23. And I know that the slope here is negative 29.3 because the value of the shear is negative 29.3. Another one, I'll just do this real quickly. We have the reactions. And I go up 9.9, over, down 28, over, up 23, over, down 6, over, up 1.1. Again, start at 0, end at 0. I'll let you add those up. Then I break it into areas, area 1, area 2, area 3, area 4. You can pause the video and see that those are the calculations of the areas. And So using these areas, I go up to 29.7. I go down 36.2 to take me to negative 6.5. I go up 9.8 to take me to 3.3. Then I go down 3.3. Takes me back to 0. And again, when I look at this, what do I see? So I can immediately look at this and I say, oh, here's the location where I have the worst shear. So it's in this region. If it's beam's going to break and shear, it's going to be in that region. Now, what about the moment? Oh, the worst moment is right there. So it's this location right there that I have to worry about. So that's, again, the beauty of the shear and bending moment diagrams. Here's another example. I'm just going to let you do... Oh, never mind. That's the same one. Okay. So let me just erase that. Okay. So remember the rules. Here are the rules. The slope of the moment diagram equals the value of the shear diagram. The value of the moment diagram is equal to the area of the shear diagram going left to right. You need to know these so you can do these problems. All right, we have done point loads. I now want to do a uniformly distributed load. What is the impact of that? So let's go through the same methodology. So let's just say that I have this problem. The beam has a length of 15 feet. I have 3 kips per foot. Now, what is that total load there? The total load is going to be 3 times 15, which is 45. Now, I just want to make this comment that in getting the reactions, everything is symmetric and uniform in this problem, and so you should also look for shortcuts as long as you make the shortcuts correct. Is if the total load is 45 kips and everything's uniform and symmetric and everything like that, well, then I can get these reactions very simply. I get half going to this side, half going to the other side. So I simply take the 45 kips total divided by 2. I get 22.5 kips there and 22.5 kips there. Perfectly acceptable to do that when you have a problem this straightforward. There's no reason to make it more complicated. Okay, so I now know the reactions. I'm now going to make this cut here at a distance of 3 feet from the left end. So if I do that, then this is my free body diagram. I have my V, N, and M whenever I make a cut through my beam. I'm going to let's take the sum of the forces in the y direction first. And when I do that, well, first thing is I convert that to a point load. It's 3 feet times 3 kips per foot, so that gives me 9 kips. Gives me 9 kips right there, and so I take the sum of the forces in the y direction equals 0, and that means, so I'm looking at this. I've got this 22.5 there, I've got the 9 there, and I've got the V there. So I've got 3 of those things. So I have the 22.5 minus the 9 because it's going down, minus the V because it's also going down, and I solve for V. I get V is equal to 13.5 kips. I can take... That's what I want to do. I want to solve for V. I now want to solve for M. So I'm going to solve for M. And I'm going to do that by taking moments about point C. So I'm calling this point here point C. And so I have that reaction. I've got that 9. And I've got that M when I'm taking moments about C. And that means you should all be able to do this, taking moments about point C. Again, that's clockwise, so it's 3 times 22.5 and positive. That's counterclockwise, so it's going to be minus 9 times 1.5. It's in the center because it's a rectangle. And then this is counterclockwise, so it's minus m equals 0. I solve for m, and I get m is equal to 54 kip feet. So at a cut at 3 feet, my answer is v is equal to 13.5 kips, and m is equal to 54. If I were to make a cut at 6 feet, so in other words, if I were going to make the cut there, around point D, I'm going to let you do this one, but I would get m is equal to 81 kip feet. Same thing, but same calculation type, but I'm going to let you do that. And I could make cuts at all different locations. I'm not going to go through all the different ones, but I can make cuts at 1, 2, 3, just, all of these values of x, and I would get different values of v. And for the we made a cut at 3, we got m equals 54. We made a cut at 6, essentially, we got an m equals 81. And I'm going to encourage you to pause the video and fill in the rest of the values of m. And, okay. So I'm going to let you do that by making cuts at all these. In other words, define the value of m. At 9, make a cut at 9. Fill it in. Using the same method we did. All right, if we do that, this is what we would get. So I'm going to plot up the values of v that we got, and I'm just going to refer to it. We made, well, let's look at it. We can, what do we notice how this is? It goes from 22.5 to 19.5, 16 point. It drops by 3 each time, and which makes sense because we have 3 kips per foot. You'll see it when you do the calculations. And so what happens is it starts at 22.5, gets lower and lower and lower, and then it hits 0 here, and then it keeps going to negative 22.5. So that's what the shear is at all the different values of x. So what do I end up with? So it looks like this. I start at 22.5 and it keeps dropping a value of 3 each time to end up at negative 22.5, and I get that. For my m, I already did 2 of these for you. I got the 54 and I got the 81. And if we kept on going, for other points, what you should get is a shape that looks like that. So you're going to get points that go up like that. We get a peak that actually corresponds to that point, and then it comes back down to 0. So if you did that calculation, that's what you would end up with. All right, now, we're going to learn one new thing from this. So what does this illustrate? Now, I'm going to do this derivation later, but for the time being, what I want you to know, and we've sort of verified this, and that is, this is sort of our third rule, and that is that the slope of the shear diagram equals the negative value of the distributed load. So what does that mean? The distributed load is 3 kips per foot, and my slope of the shear diagram is negative 3. That's what we learn. That line has a slope of negative 3. Why? Because we have 3 kips per foot pointed downward. Okay, so in other words, the way to do this, the way that we can do this is that, like I said, we follow the arrows to get the shear diagram. So when I draw my shear diagram, so here's the shortcut method. So the long way to do these problems, in a sense, is to make cuts. Making cuts always works. It just takes time. So we meant, if we made 10, 15 cuts and calculated out the shear and bending moment at each location, we can get our shear and bending moment diagram. But the faster way to do it is to do the shortcut method. I start at 0 with my shear diagram, and what does this say? This says go up 22.5, so I go up 22.5. Then, the way to do this, the easiest way, is this total load we've already decided is 3 times 15 is 45 kips. Okay, so if I go from, I'm at point A, so I'm at A, and I'm going to go over to B. And that means, and since these arrows are pointing downward, that means I'm going to go down. Well, I'm going to go down how much? I'm going to go down 45 kips. So I'm here at 22.5. I'm going to go down 45 kips, which takes me to negative 22.5. So I have this point on my left, I have this point on my right. How do I get there? Well, it's a straight line at a slope of negative 3. I just connect it with a straight line. And then what does this tell me to do? That tells me to go up 22.5. I'm back at 0. So the way to do this is start at 0, go up 22.5. Go down 45 at a straight line, and then go up 22.5. Now we're going to see this shape over and over again, so you need to know it. So know this simple, know this shape, all right, because we're going to see this one over and over again. Okay, so now let's do the moment diagram. Now, remember, we do the areas. There are different ways to do it. One way, in other words, the way that I like to do this is I have a triangle here. Let's get the area of that triangle. It's 1/2 the base times the height. So area 1, 1/2 the base times the height, so it's 1/2 7.5 times 22.5. That gives me 84.375. So we know that the value of the moment diagram, on the moment diagram, is equal to the area. So going left to right, so I'm here. I've got all of that triangular area. And then, what do I know? That this area 2 is the same as area 1. So it's going to be negative 84.375, and I end up there. So I start at 0. I end up here. So now I now have 3 points on my moment diagram. So I've got that point, I've got that point, I've got that point. How do I fill it in? Well, the way to do it is to recognize again that the slope of the moment diagram is equal to the value of the shear. So the slope of the moment, well, let's look at the value of the shear. So the value of the shear here is 22.5. So I know that the slope is 22.5. I'm just drawing a very steep slope there. The value of the shear here is 0. That means the slope there is 0. The value of the shear here is negative 222.5. So I'm draw another very steep slope, negative. Once I recognize that, then there's only one way to connect all these slopes. It's got to be like that, with that sort of shape. We're gonna put equations on this later, but that is the way that you should draw this. Now, if you need to get an intermediate value from, for instance, if you need to get what is the value of the moment at a distance of 3 feet, I can get it directly from the shear diagram. And I get it from the shear diagram by figuring out the area of this trapezoid here. And the area of that trapezoid, well, I need to get that value there. And I can get that by, I go down 9. Why do I go down 9? Because I go down 3 feet. I got three kips for each foot, so I go down 9 for 3 feet. In other words, I'm over 3 feet, I go down 9. So that takes me to 13.5. And so the area of a trapezoid is right there. It's, the 22.5 plus the 13.5 divided by 2 times the width, which is 3. So I get that value of 54. So I can get any of the intermediate points on my moment diagram simply by getting the area or areas on the shear diagram. Okay, so what I want you to do is know this shape in both ways. So I have my uniformly distributed load, so that gives me sort of this bow tie shape in a way. And then basically an upside down parabola for my moment. You need to know that because we're going to see it over and over and over again. So know this shape. Okay. All right, I'm going to stop there.